Okay, so just to finish this section on buffering, last time we saw the comparison between the implementation with no buffers and the implementation with output buffers. That was before, and then we saw also this one. This was the bufferless implementation with output buffers, that is here. We say that the implementation with output buffer is able to reach the throughput equal to 1. Implementation with input buffers instead is not able to reach throughput equal to 1. And when the size of the switch tends to infinity, the maximum is 0.586, which is less than what is reachable without buffers. So what is the advantage of having the buffers? You see it here, where you have the loss probability, packet loss probability plotted against offered load. And the packet loss probability in the bufferless case is very high for any value of offered load, while with input buffers you can achieve a fairly low packet loss probability. And this was another comparison. The analysis about throughput can be done also in the shared buffer case. With complete buffer sharing, the cells are stored in a common buffer. That is one of the possibilities that we have covered last time. And also in this case we can achieve a throughput equal to 1 because we have basically the absence of the head of the line blocking problem. And this is the comparison between in terms of overflow probability, or in other terms cell loss probability in the complete shared buffer case as a function of the buffer size for different sizes of the network of the switch. And here you can see the limit for n equal to infinity, which is this first curve, where the packet loss probability gets quite close to 0 just with a very small buffer size. So then if you want to go through the analysis of the input buffering and the output buffering, you have them in the slides, but it's not required. So as a final as a final topic, I would like to quickly go through the input buffering switch, and more in particular some elements to design a virtual output queuing mechanism. Because as we have seen, the buffered switches have the output buffered switches have optimal delay and throughput performance for all kind of traffics, because throughput can reach 1, but you need the speed up, so they are not efficient in terms of cost. Input buffered switches are desirable, but the only way to increase throughput is to use a virtual output queuing architecture, because otherwise you have the problem of head of the line blocking. And also in any case of input buffer switches, both in the simple FIFO architecture and also in the virtual output queues, you have the problem of arbitration. So you have there are a number of cells or packets which potentially can be transferred to the output in case you have output port contention, but you can transfer only one for each input-output pair, because the switch has no speed up, and therefore you have to decide which one of the potential cells that are containing can be transferred and which instead have to stay in the buffers. This is the basic scheme where you have a simple input FIFOs, and in this case the cells contending for the outputs are the head of the line cells, which are a maximum of n, since you have n VOQs at the input, and then you have to decide which one to transfer to the output port. And we know that the maximum throughput that you can achieve is 58%. So with virtual output queuing, you can avoid the head of the line blocking, and this is the scheme. In this case, when you have n VOQs for each input buffer, and these are logical queues. Since now the head of the line cells can be picked out of each logical queue, the contention and the arbitration is not between n, but n square potential cells that are contending for the output. So scheduling mechanism gets a little bit more complicated than in the case of input queuing without virtual output queuing. So for each input you can select, you can have to arbitrating between n potential contending cells, and then you have also to arbitrate between n potential contending head of the line cells for each output, because basically in each input you can physically transfer only one cell at a time. So if you have different cells here, you have to choose one, but also for each output you can transfer only one cell. So for this, for example, for output 1 you have a buffer in the input data structure 1, a buffer in the input data structure 2, and so on and so forth. So potentially n cells that are contained into output 1. We can label the cells according to their queue where they are allocated. So since in here we have n square virtual output queues, we can denote each of these queues by these two indexes. One is the input and the other one is the second is the output port. And so in queue ij means the logical queue which stays at input I and is queuing cells that are demanding for output j. So we have to transmit the cells, but we are constrained by the absence of the speed up. So at most one cell among the ones that are contending for the certain output port can be transmitted, and also among the cells that are queued in the same input port. So also in this case we can define a certain set of stochastical processes that are able to characterize the arrival of the cells as a generation process. So if you fix each time slot, there is at most one cell that arrives at each input, and we can also denote the length of the queue, which is associated to the buffer Qij as Lij at a certain time t. Aij at a certain time t denotes the arrival process of packets or cells from input I towards output j. The arrival rate, the average arrival rate is a parameter lambda ij. And now we can translate the two conditions that I mentioned before in relations on these arrival rates ij, lambda ij. So the set AAT is admissible if the sum of lambda ij on all the queues located at input I is less than 1 for each j, and when the sum for j that goes to 1 to n of lambda ij with for each input for each I and summing on all the j's is less than 1. And this is the condition on the output. So this is the condition on the input that tells you that no more than one cell can be transferred from an input port towards the outputs. And this is the condition on the output that tells that no more than one cell can be transferred to the output port in each time slot. If these two conditions are not fulfilled, then the set of cells at a certain time t is called to be non-admissible, otherwise it's admissible. Then we can define a matrix that is called Sijt, which represents matching at the time slot t. And in this matrix, if an element is 1, it means that the cell ij, which is located in the queue, the top of the queue ij, can be transferred from I to j, and 0 otherwise, if a cell that is at the head of the queue ij is not transferred to the destination. Cell arrival is an independent process that allows to satisfy two conditions. Cell at the input ports are independent and identically distributed, and the arrivals at the input port are independent from other input ports. And if the arrival rates are equal, so any destinations are uniformly distributed, it means that each cell has an equal probability to be destined to a certain output port. The traffic is also said to be uniform. What is the throughput? Is the average number of cells that you can transfer in a time slot, considering that you have an n by n switch. So in theory, you should be able to transfer n cells. In that case, you have a throughput equal to 1. Otherwise, if you're not able to transfer all the n cells, some of the output ports will remain idle, and this decreases the throughput. Another important parameter is the delay, which is the time experienced by a cell, the average time that is experienced by a cell from the arrival to the switch to the departure. A switch is stable if this is always fulfilled, that is, the average value of the lengths of the queues is constrained and is not going to infinity. Otherwise, you have that the queues start to, or at least some queues start to fill up, and then you start having losses for overflow. So it can be proved that if there is a switch that is stable and under an independent and admissible input traffic, the switch can achieve 100% of throughput. So it is. The problem is how can we optimize the decisions of which cell has to be transferred to the output port in order to maximize the throughput. And this is basically the task of the scheduling mechanism for virtual output queuing switches that is able to select the cell that has to be transferred in each time slot. In order to apply techniques, mathematical techniques that enable to solve this problem, we can refer to a bipartite graph. Basically the state of the input and the outputs of the switches can be represented by a bipartite graph, and the graph has n nodes that are representing inputs, input ports, and n nodes that are representing output ports. So this is basically the graph that we need. So if we have an n by n switch, here we will have n nodes at the input row column, n nodes at the output column. And then we, in the bipartite graph, you have always edges that are connecting a node in the first column with a node in the second column, never edges that are connecting nodes within a column. And so, what can what an arc represent in this kind of graphs? Basically, it can represent two things. The first is connection request. So when a cell arrives at the switch and it has to go to a certain output port, then we have a graph in the an arc in the bipartite graph which represents the requests. And then we can also use an arc again to represent cells that are actually transferred in a given time slot. So there is another graph that represents the cells that are actually transferred. How many cells we can transfer? Clearly, we can transfer up to n cells because this is the maximum of the capacity of the switch. But then we have to take into account the two other constraints of stability that tells that in a given time slot you cannot have two cells that are leaving a node in the input, and you cannot have two cells that are arriving to a node in the output. So basically in this graph that represents the requests, you can have degrees, the nodes can have degrees that are greater than 1. But when we want to represent cells that are actually transferred, you will have only nodes with maximum degree 1, because each input can release one cell at a time, each output can receive one cell at a time. And the responsibility of the scheduler is to find a feasible matching in each time slot. Obviously matching that tries to satisfy the requests, so tries as much to satisfy the request as possible. A match in the graph that represents the cell transfer is an arc or an edge that connects an input node to an output node. And each input is connected to at most one output, and each output is connected to at most one input. So potentially we have n square edges in the graph which represents the requests. But in the so we can have n square edges in the graph that represents the request, but we can have at most n edges in the graph which represents the matchings. So the role of the scheduling algorithm is to map the graph of the requests onto the graph of matching onto the map of the requests. The matching of input-output is actually a permutation because of the properties that we have already mentioned, and so it can also be written as a matrix where we have 1 if input I is matched to output J in the matching. Let's take an example. This is the graph which represents the requests that are arriving to a switch in a given time slot. You can see here that, for example, there are two cells that are in two different inputs, and they both request the same output here. And also in this case, there are two cells that are going to different outputs, which should leave the same input node. This is a possible matching, which is feasible because you can see that the degree of the nodes is at most 1. And for example, we have arbitrarily chosen this cell that is located here to go to the output, the desired output, while this other cell, which is located at the second node, will stay in the buffer. And this is the dotted line, corresponds to a cell that has not been selected in that time slot. And then we selected another cell here, and so on so far. So you can see that the set of edges in the matching is a subset of the set of edges in the request. But it's feasible because it doesn't go against any constraint. The matching is not unique. You can find many matchings for the same set of requests. This is, for example, another matching. You can see that instead of selecting the first two cells to be transferred, this one has been selected, and this one is being selected instead of the other one. So we have several possible matchings for the same set of requests. So the question is, what is the matching that is most efficient? What is the best matching we can find in order to satisfy requests? So this requires a computation and an algorithm to select the best matching. And when we are designing scheduling algorithm, we don't have only to take into account the first property, which is the efficiency, that is achieving high throughput and low delays, or in other words, select matches with more edges as possible each time slot. Because if you transfer a lot of cells, then your matching is better than in case you transfer less cells. But efficiency is only one of the features. We have also to take fairness into account when trying to make scheduling. We should not say serve all the inputs and output pairs in the same way without discriminating a certain input and output pair, which, for example, is never selected. And then also stability. So the expected occupancy of each virtual output queue should remain finite. We cannot allow one of the logical queues to increase too much compared to the other ones. Otherwise, we risk to have an overflow, which breaks the stability of the algorithm. So finding the best scheduling is and the best matching is a computationally intensive task. So we have some algorithm that allows to do it, maybe finding a suboptimal result, but with a reasonable complexity. The problem of the theoretical problem that have the optimal solution is called the maximum weight matching. In the maximum weight matching, we find the set of edges so we do the selection of the cells, maximizing the total weight of the matching. The weight of the matching, the total weight of the matching is the sum of the weights that we can assign to each connection. For example, if you go back here, we could assign different weights to all these connections. Let's say we can assign a weight equal to 8 to this, 7 to this, and so on and so forth. So, and this is what we can assign on the requests. Then when we solve matching, we will have a set of connections which are being scheduled, and the total weight of the matching is the sum of the weights of the arcs that have been selected in that specific time slot. So maximum weight matching is the solution, the optimal solution of the problem. Weights can be related to any kind of matrix. For example, we can base the weighting system on the length of the queues, or the time a cell has been waiting a specific queue. So we have longest queue first or oldest cell first. The advantage of this of solving this algorithm is that we can achieve always 100% of throughput with any admissible traffic. The disadvantage is that this problem is computationally intensive, and it can be shown that the complexity is a big O of n cube log n, which is in some cases very large. This is an example of a maximum weight matching solved obviously by inspection by hand. So this is the set of requests. As you can see, there are weights associated to each request, and this is the matching that has been found. The sum of all the weights in this case is 135, and we can assume, we can prove that you can see that this is the maximum possible you can achieve. Instead of solving the maximum weight problem, we can solve the maximum size matching. In the maximum size matching, basically the problem is the same as before, but all the requests has the same weight, and so maximizing the size, the weight in this case corresponds to maximizing the number of cells that you are transferring in that specific time slot. Also, in this case, we can arrive to the 100% throughput when traffic is uniform. And under non-uniform traffic, we can have instability and unfairness. The complexity is reduced compared to the previous case, but not very much, because it's a big O of n power 2.5. And in our simple case, this is a maximum size matching solution. As you can see, the total weight is less than in the previous case. Okay. The number of requests that have been satisfied is 4. Is like that is more than in this case, but the total weight is less, because we are maximizing the number of cells and not the weight. So since these two problems are too difficult to resolve, what is actually used in practice in the real routers and switches is the so-called maximal matching. So in maximal matching is a heuristic method, and the concept is that you start with the set of requests, and instead of providing immediately the final result in terms of the selection of cells that must be transferred, we use an iterative process. Okay? and in each iteration we can add other connections if it's possible to an initial set of connections that have been selected. We can achieve 100% throughput under the uniform traffic, not if the traffic is not uniform, but we have a lower implementation complexity. And if we want to achieve 100% throughput in all the cases, we have to, with this method, we have to use a speed up, even a small speed up factor, but speed up cannot be 1. And so in this case, we have to use a combination of input and output queuing. And it has been proven that with a speed up factor equal or greater than 2, we can achieve 100% throughput under any admissible traffic. So let's take again our example as that we saw before. This is the set of requests. Then here we have a set of iterations before providing the final answer, which is the scheduled transfer for that time slot. So all these iterations occurs in the same time slot. They are not referred to different time slots. So the request is always the same. So let's assume that in the first iteration we selected these two edges. It means that we selected two cells to be transferred. And then in the second iteration we can select another cell that adds to the other two that we have already selected. At each iteration we can add, increase the number of selected cells. We cannot remove previously selected cells, okay? Otherwise it gets too complicated. So here, for example, we selected another cell, and finally we can transfer, so at the end of this iteration we can also test other iterations, but if iterating the process gets no improvements, so we cannot add other cells, then we can finish the iterations. So the condition to stop iterations is that you cannot add another cell to the another edge to the selected set of the set of selected edges. So if we cannot add another edge, this is the final iteration, and the total weight is 45. We selected only 3 cells. Total weight is 45, which is less, even less than the maximum size. And we also selected less cells than in the maximum size, but with a much simpler process, the computational process. Since we at most can increase the number of connections by 1 at each iteration, so at least we have to increase the number of connections by 1 at each iteration. The maximum number of iterations is n, and but with some algorithm we can also reduce the number of iterations to log n, which is more efficient. I just want to show you the first of this type of algorithm that can be applied to perform maximal matching, and it's the simplest one, and it's called parallel iterative matching, and is based on the random selection to solve contentions between input and outputs. And since we have to implement this in a practical software program or hardware implementation, we need to specify exactly what happens for each iteration. And so each iteration has been, in this set of algorithms, each iteration has been split into 3 phases or 3 steps. The first step is called request, the second is called grant, and the third is called accept. And we can have up to n iterations in each time slot. So it means that we will have 3 by n steps in the total, in the worst case. So initially, let's assume that all the inputs and outputs are unmatched. And once we start to perform the first iteration, we will select a set of requests that will correspond to cells transferred in that specific time slot. So at the end of the first iteration, we have a set of requests that are already scheduled for that time slot, and a set of requests that instead are not satisfied. So in the second iteration, we will use in the request phase only the set of requests that have not been matched so far, okay? Because at each time you have to you can increase add another request, but since you cannot delete requests that have been already accepted, there is no point to consider all the initial requests. At each iteration, you only consider those requests that survived and that have not been scheduled yet. So this is an example. Here you have a 4x4 switch, the 4 inputs, and in each input you see that there are 4 virtual output queues, and the small balls, black dots, corresponds to cells that arrived and are stored in the output queue waiting to be transferred. So in this specific time slot, we have a cell arrived at input 1, which is requesting output 1, a cell at input 1, which is requesting output 2, a cell at input 3, which is requesting output 2, and another requesting output 4, and one cell at input 4 requesting for output 4. Only the head of the line cells are considered because the other ones cannot be scheduled in that specific time slot. This is the initial set of requests, which is mapping the situation that you have there. And we take this as the request step in iteration number 1. So after the request step, we have the grant step. The grant step works in this way. When an output receives requests, the output will send a grant to the input nodes, and it will send only one grant, one possible grant. So for instance, output 1 received one request, so it will send from input 1, it will send a grant to input 1. Output 2 received 2 requests, one from input 1 and one from input 3. In the grant phase, output 2 has the possibility of sending only one grant, and so we have to decide how to select the input node that will receive the grant. And since here we are in the PIM the PIM algorithm, which is based on the random selection, the choice is random. So randomly we choose one of the 2 requests, and in this case input node number 3 is chosen. The same for output node number 4 that received 2 requests and then randomly select one of the 2. And in this case, node 4 selected a request from node 3. So now what happens in the last step, which is the accept? Now is the turn of the input nodes to select which grant to accept. And the condition is always that an input node can accept at most one grant. Okay? So in this case, input 1 received only one grant, so it is accepted. and the input node 3 received 2 grants. So it has to decide which one of the two, and since here we are using random, it will randomly select one of the two, so in this case node 2. So this is at the end of the accept phase, the set of arcs that corresponds to cells that are scheduled to be transferred in that specific time frame, in that specific time slot. And you are always guaranteed that this set is stable because of the way we selected the grant and accept phase. And but this is only the end of the first iteration. Okay. At the end of the first iteration, you can see that one request from input 1 to output 1 has been satisfied, and one request from input 3 to output 2 has been satisfied. So if you take the initial set of requests, okay, we can obviously take off the request 1 to 1 because it has been satisfied, and also the request 3 to 2 because also it has been satisfied. But we can also eliminate request 1 to 2 because since here we have decided that to accept this request, this input will be engaged in the in this time slot to transfer one cell, and then it cannot transfer a second cell. So this request will never be granted in any iteration. The same for input number 3. Input number 3 will transfer a cell from this node to here, so this request cannot be satisfied. But we have still one request on the original set that potentially can be satisfied because node 4 and node 4 so far they have not been engaged in any transfer. So we can do another iteration where we will consider only this request. Okay. And so now this here I don't show the other iteration, but it's quite obvious that also this request will be accepted because we will have a single request and a single grant and accept. And so finally the three selected cells are these three that we have seen here. Each iteration resolves on average at least 25% of the remaining unresolved requests. So the algorithm can converge in the worst case is taking n iterations, but on average it will take only log n iterations. So it's an effective algorithm, which however has some problems that I'm going to show next. It's quite simple because it requires no memories to save the states of the nodes, because each time the selection is random. So in the grant phase, if we have selected at this iteration node number 1, then we can forget it. We don't need to remember this selection. And so each time we start a new iteration, all the selections begin over, independent of the last iteration. This is not the same for other algorithms that are more sophisticated. What is the advantage of this kind of algorithm? In one iteration, the throughput is very low. On average, is about 63%. And also the random selection may behave in an unfairness way for some traffic patterns. This is unexpected, but it's like that. And for example, if you consider this case where you have this set of inputs and so 2 cells at the first input and 1 at the second, and the first two cells are containing for output number 1. On average, the throughput will be different for the different traffic flows, and in particular, you will have 1/4 for one for the connection from 1 to 1, and a half from 1 to 2, 3/4 for 2 to 1. Why this? This is wrong in the book, so be careful. You can explain this with this example, with this egg-based figure. So assume that you have the set of requests as previously depicted. So you have one request from node 2 to node 1, which is colored in green, one from 1 to 1, 1 to 2, which is in red, and one from 1 to 1, which is in blue. And instead of considering let's say random inputs, let's assume that you have this pattern for many different time slots, one after the other. So this is the sequence of requests that you have in many time slots. So you have always the red request, the blue, and the green. So let's assume that the deterministic, the decision, instead of being random, is deterministic and alternate, instead of being random with a uniform probability, which is practically the same. So this is the request phase. Now we have the grant phase, and in the grant phase, the red request will be always granted because it arrives to the output node below, which receives only one request. Instead, the output node above has to decide between two different requests, the blue and the green. And we can assume that it alternates between the blue and the green. So the result is this one that you see, the result of the grant phase. And then we can combine together this set of grants, because what is the situation? Okay. So after the grant phase, then we have the accept phase. Okay, and in the accept phase, now the green is always is received. The green grant is received by this node here, the input node, which receives only one grant, and so it will always select that grant. And then here, this input node on the top receives two different grants, and again it will select between 1 and 2 in an alternate way. So in the first time it will receive a blue and a red, and it will decide for the blue. Then it will receive a red, and so it will decide for the red, of course. Then again receives a blue and a red, and this time it will decide for a red. Then again the red, then blue and the red, and we decide for the blue, and so on. So this is the result of the accept phase. And that corresponds to this sequence that I have shown here. Okay. So at the end, what happens is that the number of times, if you count the number of times that you see each color, the green color is found a half of the time slots. The red color is found on the 3/4 of the time slots, and the blue color is found 1/4 of the time slots. So this is why this protocol is unfairness for this particular traffic pattern. So how to make it fair? We have to use a more sophisticated algorithm, and for example, we have the iterative round-robin matching and other kind of algorithms. All these algorithms, differently from the random we have seen, requires that we store the state of all the nodes. Okay, so the input and output nodes. Now I stop here because I don't want to go more. So you can study until this the first random algorithm, the PIM, and if you want, you can have the look to the other algorithm, but they will not be required. And so this is basically the final slide of the course. I don't have already uploaded this final set on BIP, but I will do it soon. And so